Mm. That should be there somewhere. No. No. The other column. Well, technically the only one. So. Well, you're here. Fine. Sorry. I don't know where it would be. Probably on my desk. Or somebody else took it. Sorry, I got you. Pretty with me. I think I got most of it. Pretty good with me. Oh, where was it? You didn't hand it back yet? Unbelievable. One minute. All right, it's 11 o'clock. We're going to get started. All right, here we go. Lord, thank you so much for bringing us together this morning. Thank you for everything that you do for us and all the blessings that you've given us. I pray that you would continue to help us through this summer session, help us to stay focused on our reasons why we're doing this and the big picture. In your name we pray. Amen. All right. How's everybody doing today? All right, I got one fine and then a bunch of mumbling. Let's try that again. How's everybody doing today? Wow, I think that's a little bit exaggerated too, but thank you. Appreciate it. Let me ask you guys a question. What time is it? I was hoping you would say static time because that's the wrong answer. And I just wanted to see how many acolytes of Tomford are in the room. I know, this is horrible, right? It's game time, guys. It's game time. Let's go. Anyway, it's 11:01. All right, here's what we're going to do today. We are going to talk about the water tower product plan. Why? Because that's due next week. And it seems like it's a pretty good idea that you guys understand what my expectations are to be able to do that assignment to the best of your ability, right? Then we're going to jump into topic 2, which is equilibrium of a particle. We are a little bit early on jumping into that. I've basically taught you everything that you need to know for homework 1 at the end of last class, right? You should be able to do it. If you haven't started homework 1 yet, it's a choice for sure. Next time, start sooner, okay? Next time, start sooner. Then we're going to start talking about free body diagrams, 2D equilibrium, 2D systems of forces. So we're actually going to get into more of the actual statics stuff and less of the pure math stuff, right? But first, vectors are confusing. Well, it's gonna be a long rest of the 6 weeks, guys. So I hate to tell you. It's probably unit vectors. All right, so what is important to know about unit vectors? There's a couple of things. The very first thing is that a unit vector is useful because it runs parallel to another vector, right? The most common use of a unit vector that we have are x, y, and z coordinates. The x, y, and z coordinate axis frame, or I, j, and k, are unit vectors, right? That allows us to break any vector that we have into Cartesian components. We are keeping it really vanilla in terms of coordinate systems in this class. We will talk pretty much exclusively, and by pretty much I mean 100% exclusively, about Cartesian coordinates, right? X, Y, and Z. We're not going to talk about polar. We're not going to talk about cylindrical. We're not going to talk about anything crazy. However, if we were, that's just a different way to map things from Cartesian space, okay? So everything is up, down, left, right, and in and out of the board, right? That's what we're dealing with. And those are I, J, and K unit vectors, and they are super important because they allow us to determine directions, right? They give us directionality of things. And so if you have a unit vector and you have a magnitude of a force, if you multiply those two things together, remember a magnitude is a scalar and a unit vector is a vector which has a direction, right? But also a length of 1. So when you multiply anything by 1, you should get itself, right? And that's what allows us to use that definition to get different force vectors, right? But what we really like to use them for is to create a unit vector out of distances, right? Because the unit vector, regardless of whether you make it out of force, distance, velocity, acceleration, moments, whatever, the unit vector it's always pointed in the same direction, right? As long as you're pointing in the same direction as your force, it becomes really useful. And when does that happen? When we're talking about cables, when we're talking about chains, when we're talking about things that are connected by some other system and we have to have some force that connects them, right? So if you have train cars, right? Those are all connected by a hitch, right? Those hitches are going to direct your forces along the other train car, right? If you wanted to, and it'd be a horrible idea, but you could put a cable between your train cars, right? And start pulling them. The dynamics of it would not work out, but the statics of it would work out, okay? Once you start going around a curve, that thing's not going to be rigid enough to hold your train. Anyway, kind of a tangent. Foam noodle. Yeah, that was, I don't know, they took it from me. It was here, and now it's not. I didn't bring it back to my office. I had assumed that the lab staff left that for me, just for reasons. Okay, redrawing. I would recommend always redrawing your any diagram that you're given. Especially today, we'll talk about free body diagrams, and we'll talk about why it's important. 3D angles. Yeah, no, that's super confusing. I agree. That's why I tend to not work with 3D angles, and I try to work with unit vectors as much as possible. Right. Remember, the best thing about vectors written in 3 dimensions is that you get a set of coordinates telling you exactly where they go, right? It is a map. It is, I go this far in the I go this far in the J, I go this far in the K, and you draw an arrow between those 2 points, but a day. Okay? All right. Vector planes. So vectors as they, so all right, so in aviation, right, a vector is your line of travel, right? And you'll hear folks from the Air Force or commercial airline pilots about their vector. It's just a magnitude and a direction, but I'm pretty sure that's not what you meant by writing vector planes. Vector as it applies to the plane, like XY plane, XZ plane, YZ plane, right? That's a nice way of looking at some vectors, right? So remember, you can always use tools like visualization tools like MATLAB or SolidWorks to draw what your vector looks like and then rotate it in 3 dimensions, right? And so if you look at something in the X, Y plane, you might be able to get some information that is very helpful, right? So like if you know the angle off of the XY plane to a vector, if you look at it just in the XY plane, that angle then becomes a right triangle, right? And you can get your components. Okay. What else? Vectors was the big thing, though, for sure. Visuals. Yeah, so some people are super visual learners and some people aren't. I try to do the best I can. I am limited in my skills as an artist, even though I do have a master in fine arts from the Michael Scott School of Business. So, anyway, okay. Where is that? It's online. I did the online program. Um, all right. Any other, so is there anything that you guys feel like I absolutely need to cover before I clear this? Is everybody feeling okay about vectors-ish right now? Yeah? Okay-ish? I'll settle for okay-ish. That's fine. It's been a long week for sure, right? There's a lot of, you know, we recognize that you have many options in your statics education. We appreciate that you picked Grand Canyon University. I think this is going to be hysterical when people watch these videos because all of a sudden there'll just be like applause for apparently no reason and nobody will get it. All right, I'm going to clear these. Okay. So before we move on, I'm going to go row by row. What is one thing that we remember from last class? And we'll start in the front row. Anybody, one person from front row, tell me one thing that happened last class. Unit vectors, great, thank you. Second row, what's one thing then you can't say unit vectors? That's how this game works. You're not in the second row, Colin. Lose all the points that Ryan just got you. All right. Excellent. Thank you, Isaac. Next, third row, what's something that we learned last class? They're all not looking at me. Yeah. We're gonna go with Aaron. Aaron, what's one thing from last class that you thought was particularly interesting? Position vectors. Okay, cool. Next row, we got somebody. All right, well, we're gonna go with Ian. What's something from last class? All right, dot products, cool. And the back row, we got one thing that you guys learned from last class, one thing that we covered. Can be anything. Yeah, Jason. 3D vectors, excellent. All right, awesome. Cool. Now is the time where I ask you to convert the temperature. No, just we're not doing that. All right, so last class we stopped off on this problem. I told you we would come back and we would hit it. So this is going to be our last dot product problem. All right. Let me find my pen here. So what is this saying? Right, this is have the magnitude of the projected. We want to find the magnitude of the projected component of f along AB as it is, well, all right, let's start over. The magnitude of the projected component of f along AB is equal to the dot product of f and the unit vector. Okay, so what is it asking us to find? It's not really clear there. It wants us to find oh boy. It wants us to find the force, right? It wants us to find the force F. All right, is that what it wants us to find? No, it wants us to find FAB, sorry. It wants us to find FAB, okay? And it wants us to find F perpendicular to AB, okay? That's those two things there. So, well, we need to kind of know something, right? It turns out that we know F. It's just not written down here anywhere. So F is going to be 300 newtons. What direction should I put on that? I'm asking the questions here. J hat, yes. Right, it is, looks to me, right, that goes just straight to the right, right? Best we can tell. Whenever you're doing things by visual inspection, we're always aiming for the best that we can tell, because your eyes are great, but they're not infallible. Okay, great. So we have that. Let's back up though. This seems really complicated because it says things like projection and things like that. So whenever we hear the word projection, our minds should probably go to a dot product immediately, right? Why? We talked about it at the end of last class. Another way to think about a dot product is, and that's when I use the foam noodle, right? Put it on there. You can see the projection of my shadow on the board, right? If you're standing at different angles, it looks different. But if I move my arm, it's taller or shorter depending on where I am with respect to that light, right? Same deal with this, right? If I want to project a vector onto an axis, that means I want to know how much of this comes down on there, right? So I'm just trying to find the components. It's different because it's not necessarily nice and Cartesian, right? Not necessarily. Okay. So where do we start with this? There seems like there's a lot of missing information. I mean, we're given a bunch of distances here, right? You can kind of see from A to B, and then, B is kind of out there in space somewhere. It's not in the X, Y, X, Z, or Y, Z plane, right? And so it's kind of coming out here. Look at this. Right, so 6 meters from A over to B, right? You've got this offset from the y-axis of 2 meters. And then this obviously travels upward, and that's 3 meters upward, right? So we've got positions, okay? Whenever we're given positions and minimal information about force and no angles, right? We should probably be looking at unit vectors, right? So let's make a unit vector from A to B, okay? So if I want to make the unit vector from A to B, which some people call lambda, but we've been using U, so we'll just use U. What is it? Well, it's the position vector from A to B divided by the magnitude of that vector from A to B, right? So if I'm going to travel from A to B, how do I get there? What is RAB? 2I, 6J, 3K. Everybody agree with that? The units on that. Meters. Perfect. Okay. Yeah, because everybody see that? We like to report them in X, then Y, then Z. You don't have to, but it's helpful. The video we watched last class kind of showed coordinate form for vectors, right? So you could write this in parentheses as 2, 6, 3, and just get the coordinates from it, assuming that you're starting at the origin, right? But we'll write them in Cartesian format like this. Okay, what's the magnitude of this? Yes, which is very obviously, without having to pull out a calculator, 7. And that was a joke. It's not very obvious. I mean, you could just do the square. 4 plus 36 plus 9. 49 square root 49, 7. Check. Okay. So that means our unit vector, U, A, B, is going to be 2/7 I plus 6/7 J plus 3/7 K. And I think last class, and that should be meters divided by meters, right? So it's unitless. Okay. Last class, we said you can feel free to either actually take the fraction if you want, right? Make it a decimal or leave it a fraction. It's up to you. In this case, I'm going to leave this as a fraction for the rest of this. There's really no rhyme or reason to how my brain chooses whether to use a decimal or a fraction. Most people will agree that using a fraction gets you better resolution in your final answer because there's no round off error in a fraction, right? 6 of one, half dozen of the other. But if you're noticing that answers aren't coming out the way you think they are, maybe try doing it fractionally instead of with a decimal. Okay, that's great, but we want FAB. Okay, so how do we get FAB? Product of unit vector and F. So like, let me see if I got you. So if we're going to look for FAB, we want F dot UAB. Is that what we were saying? Yeah. Okay, cool. How'd you come to that conclusion? You did. Excellent. Reading. Okay, excellent. So, well, we got to take dot product. Looks like we have two vectors, so we should be able to do this pretty easily. And this one's not too bad because one of our vectors is what is called a singleton vector, meaning it only has one component, right? If you wanted to write out all three, that's fine. And I'll do it long form since we haven't been doing a lot of dot products to start with. But, I think you guys will see what I mean. So FAB is equal, well, F is this, right? A lot of zeros in there. And I'll use square brackets just to separate them for now. And U we just came up with was 2/7 I plus 6/7 J plus 3/7. Okay. Okay. First of all, I want you to recognize something right off the bat. Anything that I multiply by I and K is going to be 0 regardless because it is 0 already. Okay. So right off the bat, we know that even when we get to 0 times 0 I dot 2/7 I, that's 0 times 1, which still 0. So really, with a singleton vector, that's why I'm saying you don't need to go through the process of everything, right? But what we'll end up with is 0 plus, well, 300J times 2/7 I. That's 0, right? Because remember from dot product rules last class, and what Isaac told us a few minutes ago, is that the only dot products we really need to worry about are I dot I, J dot J, and K dot K, because those are the ones that give us our 180 degrees or our 0 degrees. Okay, so it's 300, put it in parentheses, 300 times 0, all right, plus 300 times 6/7 plus 300 times 0 again. All right. Plus 0, because 0 times everything is 0. And so what we're left with is just 300 times 6/7, which is a cool. And remember, this is a magnitude, right? This shouldn't be written as a vector because it's a dot product. It's a magnitude. That was my bad. 257.1 Newton. Cool. That's great. Should be Newton because it's a force. All right, and so remember, UAB doesn't have any units, and our force vector does, and so the units maintain across, which is another why unit vectors are so nice, right? Is because if we know the units on one of them, the units on the unit vector is a unity, which is 1, which means it doesn't have any specific units. Okay, well, that's great. But we only have the magnitude of FAB. We didn't find the actual vector, right? So let me do this. I'm going to clear that for a second. I'm going to leave our magnitude up at the top. You guys all done writing down that stuff? Maybe close. I'll give you a second. You know what? We'll keep this also. And we'll keep this just for fun. For fun times. Okay. All right, so that's great. I've got the magnitude. How do I find the vector FAB? What is a way that I can find that vector? Given the information that we have. Yes, Kento. Excellent. Remember, let me write it as a magnitude first. It's the magnitude times the unit vector, right? The force AB is traveling in the direction of the unit vector, right? We know that because that was a frame that we were looking at, and that was a rigid bar going from A to B. And so that force has to travel along that line of action, right? And we were specifically asked, what is the force going from A to B, right? Because of us pulling on it with F. Excuse me. So we've got 257.1 times our unit vector, which is not 3/7, but 2/7. If I can get there. 2/7 in the I, plus 6/7 in the J, plus 3/7 in the K. And if we crunch that out, we end up with around 73.5 in the I, plus 220.4 in the J, plus 110.2 in the K. Everybody cool with that? Tracking with that? Maybe. Ooh. Yeah. Any questions on this one so far? There's one more thing we're going to do because we didn't find F perpendicular yet. If you guys are forgetting what F perpendicular is, it's this force that is perpendicular to FAB, pointing downward. We're looking for that. Oh, wrong way. All right, questions right now. All right, so what do we know? How are we supposed to find F perpendicular? Well, there's a couple different ways that we can try to do this, right? And one of them is much simpler than the other. So we went over a bunch of ways to determine, the angle between forces and whatnot. And that's fine if you know both of the vectors, right? And so some of you are probably like, well, I know that a dot product, I can use that to find an angle, right? But you know the angle that's perpendicular, it's 90 degrees, and the dot product is going to give you 0. So it's not really helpful in this situation, right? We're not looking for the angle. But what we do know is that F, that blue force, we'll call it F sub R, even though it says F there, just to remind you guys that that is a resultant, right? And we want to break it into its components, which happen to be FAB plus F perpendicular. So if I want to know what F perpendicular is, I can just algebra my way there and take my resultant and subtract another one, and that should give me F perp. So, right, what do we have? And I'll write it this way, just for ease of demonstration. We end up with F, right, so it's 0I plus 300J plus 0K. And we're going to subtract from that 73.5I plus 220J plus 110.2. Okay, and that should be 0.4. Right, we'll just leave that there for now. All right. So I think it becomes pretty clear to see, right? If we do it this, we stack them this way, it's just subtract the i's, subtract the j's, subtract the k's. And what we're left with is a negative 73.5 in the I direction, positive 79.6 in the J, and a negative 110.2 in the K, and that should be in Newton. Right. So there we are. And if we wanted to, we could find the magnitude of that, right? We would just take the square root of the sum of the squares of the vector, and we could find that if we wanted to. And if we wanted to find the direction cosines, right, you wanted the angles, you could do that too. Don't recommend doing that, but you could, right? Since we weren't asked for that, I wouldn't do it. But that's pretty much where we're at, right? And so we can use dot products and unit vectors in conjunction with one another to get projections of vectors onto axes that aren't necessarily I, J, and K, right? So why would that be useful, right? Why would that be useful? Well, there's plenty of times where you're going to be pulling something and you might not know the angle that you're pulling at, but you know the force. Right? I can get a force sensor pretty cheap and tell me exactly how much force I'm pulling a rope with, but I might not know the angle. But I also want to know how much perpendicular, what's my perpendicular force to that, right? Like what's my X, Y, and Z components for based on that new coordinate system, right? How much is going perpendicular upward from the rope? How much am I in and out of plane, right? Am I wasting any of my force by pulling to the side instead of pulling straight, right? Those are all things that would help us understand that, right? If the more, I guess, if the wind's blowing, right? In the case of statics, right? I have something hanging by a rope. And if the wind's blowing, how do I know that I have the ability to hold something in and out of plane with the rope that I have, right? How do I know it's not going to shear? Those are all some examples of why you want to do it. Yeah, Colin. Yep. Let me do this. I'll show you. I'm going to clear this. We'll go here. Go here. Okay. So we're going to subtract this one up here, FAB, right? We're subtract this and this, right? So the resultant F, the blue one, minus this one gets us this guy down here, okay? Because if you look at how this is set up, these are perpendicular to one another, right? And so, I don't know, when you guys took physics 1, right? Did you do the experiment where you have the block on the inclined plane and you raise the inclined plane until it starts to move, right? It's a similar idea here, right? When you do those sorts of problems, you tend to turn your coordinate system so that it's in line with the inclined plane, right? What we did here was the harder version of that. We kept our coordinate system fixed to point A instead of turning it. I've told you before that these are arbitrary choices, and that's true. We could have turned it, and this would have been just a simple Cartesian thing, right? Except that without any angles and based off the distances that we have, it's a lot harder if you rotate that, right? So context from the problem is key here. It's understanding when we want to change, when we want to change our coordinate system, and if that's even possible given the information that we have, right? Okay. Yep, no problem. Here's what's due tonight. Please do that homework by 11:59:59 and 0.99 seconds or 0.9, whatever. Just do it. Do it before it's due. Then there's a homework due next week on the 15th. Then next Sunday is your water tower product plan. Then we have a quiz the week after that. And then we have another homework the Sunday after the quiz because I didn't feel like being really, I didn't feel like being a jerk to you guys and having you have a homework due on the night of a quiz. So anyway, here's the Dr. D-ism for the day. Don't be afraid to sacrifice points on small assignments for gains on larger assignments. For example, how does getting 100% on every homework help you if you checked it, right? You don't know how to do it, and then when you get to the quiz, you don't know how to do it, so you don't do well, right? Turns out that learning is the whole thing about learning is making mistakes, right? Not to get morbid about it, but life is a series of mistakes, one after the other, and you need to learn from them. And so please, start your homework early. Don't start at the night of. Come ask me questions if you get stuck on something, right? Just be, and don't, getting a few homework questions wrong and learning how to do the problem is going to serve you a lot better when it comes down to quiz day, when quizzes are worth 125 points each, right? So just be aware. All right, let's talk about this water tower product plan. So what is this, right? The whole premise of this project is this is the setup. So the entire semester, we're going to be kind of working towards the end goal here. The first part of this is an individual assignment where you need to come up with a product plan, okay? So please read the description in Halo, not on Halo. Maybe it's on Halo. I don't know. I feel like it'd be in Halo. Go to Halo, read the description. Essentially, what you're being asked to do is determine and design at some point, but for this part, it's just this. You're part of a group that wants to create a water tower for an underdeveloped nation. So you need to find a place. So you're basically using this document that you're going to create to ask folks for money to fund that project, okay? This is a research-based paper where you practice convincing people to give you money, okay? Let me ask you a question before we get into the meat and potatoes here. If anybody you knew were to ask you for $20, would you just say, yeah, that's cool? Or would you start grilling them? Well, what do you need the $20 for? What do you, like, I'm probably be like, well, my son comes to me and is like, well, I need $300. I'm like, well, what's that for? I want a Nintendo Switch. I'm like, well, that's not enough. That's not enough money. That's not, like, yeah. Why should I get you a Nintendo Switch? Well, I've done this product plan and I can show you exactly why. Which would be a great answer, but it's because I want one, which is less likely to get you the Nintendo Switch, right? So now let's extend this to a public works project. I don't have the money to fund the building of a water tower. So I need to go out to other groups and convince them to give me thousands, maybe millions of dollars to fund this project. How am I going to do that if I'm weak on my reasons, right? And the most commonly missed items from this project are a proper mission and vision statement, and this is a big one, the actual human value proposition. So this is tied into a Christian worldview basic, right? So first, mission and vision need to be specific. Hit me over the head with it, okay? Our mission is to, what is your mission, right? Achieving blank is our vision. We need to have both of them. Remember, mission and vision, in Halo, it says that the mission and vision statements are clear, concise, and logical, right? So the logical part, sometimes people forget. Like, you can't just be like, our mission is to make a water tower. Like, but why? Why do you want to make a water tower, right? Concise. Don't make it, it's like 1 to 2 sentences for your mission and your vision each, right? Don't belabor. I think a good litmus test for this is if you read your mission and your vision to somebody who is not in this class and they understand exactly what you're trying to tell them, you've probably done it, right? If you can talk to somebody who has no idea what this project is about and clearly describe what you're doing to them, and they get it, you're good, right? So, like call your grandparents, maybe your parents, right? I don't know. Tell your cat. All right. The next part is market identification. So, great, you want to build a water tower. Where? Where in the world? You're gonna build it, I don't know, in the city of Atlantis? Probably not a great choice. There's lots of water there currently. So find a real place that could benefit from my water tower and cite your sources, right? Identify why. Why is it important for this location to have a water tower? What does it provide to that area? Okay. Human value proposition. This really is the most important part, right, of this, right? And so again, human value proposition. A lot of students will just throw like a couple Bible, like we should just, or anyway, we'll get there in a second. It needs to include your values, okay? So how many lives are impacted by your water tower being there? How much money does this community end up saving? What kind of socioeconomic factors get brought? Did you create jobs because there's a water tower there now? What other improvements go along with having the water tower? Winning formula for this. Our invention will save X dollars in healthcare burdens. Cite a source. An investment of Y dollars will yield Z dollars in return in GDP. Cite your source. Our invention will create N new jobs, right? Again, cite your source. This is the research part, right? So don't just tell me we're going to see 100%. Woo! We'll have 100% increase in jobs. You gotta tell me more than that, right? Um, Cite a source. Well, studies have shown that, De Gregorio et al. Have shown that the creation of a water tower of this size typically yields X percent of employment opportunities, right? Like you can find stuff there. Yeah, X, Y, Z, and N should all be numbers. Don't just use random variables, right? Actual numbers. Yeah. And if I have to solve an equation of your human value proposition, it has been done incorrectly. Um, sure. You can write whatever you want. It's fine. Okay. Here's some commonly missed things. Students use "we help other because God said to," which is true. Which is true. We should help other people. We should give to those who are less fortunate. However, I go back to the example with my son, which is trivial. If my kid comes up to me and says, well, it says in the Bible that you're supposed to give to other people, and so you need to give me a Nintendo Switch or the money for a Nintendo Switch. I'm like, that's true, but I don't think that that's what God meant, right? He might have. I guess I'll find out one day, just not today. 1 to 3 Bible verses about helping people as their human value proposition. Again, how do you convince people to give you money, right? This is an important piece of it because it communicates your values, it communicates potentially your vision and your mission, right? Christian-based ethics, right? But it doesn't speak to you actually having a plan on how to execute this, right? And so if you were to walk into Shark Tank, try to sell them a water tower, right? Mark Cuban's going to be like, he'll walk out of the room. Mr. Wonderful will try to lowball you because that's what he does, right? But the whole point is be specific, right? We go back to here. Numbers, data driven, okay? Okay. In the rubric, you will see that it says human value proposition is present but lacks clarity, conciseness, and/or logic. Discussion of socioeconomic effects and Christian worldview are missing. There's 2 parts there. This would be a 2. So if you look at the rubric, 1 is that you just didn't do it. Okay, that's a 0. It's really easy to grade. If the section is missing, I think if you gave it a try, but you missed part, if you missed this, like this is a big part of it, right? The specifics of, well, God said that we need to help people, and this is how we're helping these people, right? References and in-text citations are important for this. They are required. I believe it says you need to have 3 to 5. I am typically pretty lax about the number of citations. I am very concerned about the quality of the citation more than the quantity of the citation. Okay. If something in your reference list and it is not used in the text, then you need to get rid of it because you didn't cite it. Okay. If you are confused, I think it says use APA in, I think it says in Halo to use APA, which frankly I think is a trash citation, but that's fine. I would recommend E, but if you use APA, that's what it says in there. I will be happy as long as you use any citation method, frankly. If you guys didn't know this already, it used to be, back in my day, we had to look up how to do citations from a manual. Okay, like I had to buy the MLA handbook, and if I needed to know how to cite a website, I had to go through and be like, well, and then it's like, well, what kind of website is it? Is it a person? And I'm like, oh, I just want to cite this source, man. Microsoft Word has a tab at the top, says references. Okay, you can set it to whatever citation style you want, and it will spit out the correct citation for you. You don't even have, and then at the end, if you click back up there and you hit works cited, it just spits out a reference page for you too. So like use your tools. Use your tools. That's what I'm saying. Stand on the shoulders of giants, please. Don't mess up citations because you claim you don't know how to do them. First of all, I don't believe that that's true, given the demographic that we're dealing with here in this class. And second of all, there's so many tools out there that allow you to just be able to do it that let's just it becomes a laziness thing. Okay, cool. Here's an example. Autonomy is a crucial part of effective mentoring. Bromovska and Brady, 2021. And mentoring relationships that are forced are perceived as insincere. I'm not, 2019. Okay, great. And look, here's a reference page. This one is actually not in APA format. Do you know how I know? Because there's no indentation on the second line. In APA format, you have to indent the bottom half, right? The top half goes left flush, and this comes in half an inch. Okay? If you used the references tab, it would do that for you automatically. If you don't use the references tab, then you got to go up to the thing, you got to pull it over, and I mean, it's not hard, it's just annoying, right? Okay. Questions on water tower product plan? Yes, Colin. It's due on the 18th. It's a Sunday. Not this Sunday. This Sunday is Mother's Day. For those of you who hopefully didn't forget, get your mom something nice. Okay? She deserves it. All right? Yeah, anyway. It's not due on Mother's Day. I would never do it. I got my mom a thing from it's a bunch of candy today because if you wait, if you wait and won't get there on time, it's better for Mother's Day gifts to be early than for Mother's Day gifts to be late. Yeah, just in general, anybody, anniversaries, um, Christmas, birthdays, Valentine. Be early. Don't be late. Don't be late with the gifts. All right, anyway. Any other questions, comments, concerns? You guys have plenty of time. If you have any questions, feel free to ask whenever, right? Discord or in Halo or in my office or whatever. Make sure you ask your questions before Sunday night that it's due. I would recommend, in there. The next part of this is going to transition to CLC group after this. And so you guys will work as your teams to start your product design, right? And then you'll eventually have a design paper and a presentation that you guys will have to do. Presentation will be, you guys will make a YouTube presentation and submit a link for it. We'll talk more about that in a couple weeks when that opens, because that one will run for a long time. You'll see it on the calendar running from basically, I believe next week we're going to start talking. No, once the product plan is done until the end of the semester, it'll run. Yeah, fair. Yes, exactly. So yeah, everybody does their own product plan, and then you guys come together to decide in your group how you want to attack it. It could be a combination of your product plans. It could be that you didn't like anybody's product plan and you're going to do something totally different, right? So there you go. Okay, cool. Anything else? About 4. So 4 max. I'll allow less. If you really want to do it by yourself, you can. Do not recommend. But we'll talk more about groups probably after the product plan is due. So not next week, but the week after. Okay. Cool. Anything else? All right. So topic 2, equilibrium of a particle. Like I said, we're going to start with particles. We're going to start with particles. And then we'll move up to rigid bodies by the end of next week. Okay. And we won't worry about gases or fluids. Gases or liquids. We'll just worry about that. So what are the topic? Equilibrium of a particle. The objectives here are to identify equilibrium conditions, create FBDs for particles, and apply equilibrium analysis to three-dimensional systems. Whew. All right. So big picture stuff, right? I've got a crane. It's lifting this load. To decide if the straps holding the load to the crane hook will fail, I need to know the forces in the straps. How would I find them? Well, I need to figure out what this. I know the tension in my line, and I know the weight coming down. I would probably need to do some sort of analysis to figure out what the force is when it splits from these three cables, right? These straps. All right, for this spool of a given weight, how would you find the forces in the cable AB and AC, right? So the tension here and here. Right, well, we draw our free body diagram, right? Here's point A, X and Y, right? We would need to know probably an angle that this comes off at, right? Find the X and Y components, right? If you know what the tension is. FBD is hopefully should not be a totally foreign idea. You should have seen them in physics 1, right? I don't know. I've never taken physics 1 here, so I don't know how much they hit of free body diagrams, but I will argue, and I will always argue, that it is an important point of any problem, especially in this class. Okay, so we're going to do 2D to start, right? So here's an example of a 2D or a coplanar force system. When you hear the term coplanar, that is a fancy way of saying that it's dimensionals, two dimensionals. Oh man, two-dimensional. It's a fancy way of saying that. It just means that all of the force vectors exist in the same plane, right? One plane. So in this case, we just have x, y, or whatever we're going to call it. If the whole assembly is in equilibrium, then the particle A is also in equilibrium. Okay, so that's a way of saying that if the whole is in equilibrium, then all of the parts of the whole have to also be in equilibrium. Okay, to determine the tension in the cables for a given weight of cylinder, you need to learn how to draw a free body diagram and apply equations of equilibrium. Okay. FBDs. It is, again, I can't emphasize how important FBDs are, right? I think I told you on the first day, if you don't have an FBD, you're going to be real sorry when we start doing some of these problems, right? So it's a drawing that shows all the external forces acting on a particle, right? So the external forces. And it is key to being able to write the equations of equilibrium, which are used to solve for our unknowns, which could be forces or angles or whatever it is that we're looking for, sometimes distances. Okay. And it's worth a lot of points. That's really why. Like a lot of points. Like you're going to be like, that is absurd that you are going to make it worth that many points. Okay. Okay. So I've got this drum with a cable wrapped around it. And okay. First thing I want to do is I want to isolate the body of interest. It is called a free body diagram because we have removed everything except for the body that we are interested in analyzing. That means in this case, you'll notice that the cable is no longer here. we're just looking at the drum. That's it, right? Just the drum. Second step, draw your axis system or your coordinate system, whatever you want to call it. In this case, you'll see I've got X positive to the right, Y positive up, and I've put this here to indicate that that is a positive rotation. You'll see me draw this typically like this, where I've got X, Y, positive rotation that way. I take all of the guesswork out. That's just the right-hand rule. X and the Y. If I rotate that way with the right-hand rule, that's positive. Put it there. You're not going to see me doing this every time I need to figure out what a positive rotation is. All right, it's just there for me. Okay. Number 3. Add in your applied forces. Weight. I'm pushing on this with a force of whatever. Anything that is applied from an external perspective, we would add. Then we put our supports in, right? So in this case, that's our tension, right? You could argue, well, the tension is an applied force. If it's just hanging there, like for some reason, if this were hanging from the ceiling like that, which I don't know why it would be, but if it was, that wouldn't be an applied force. That would be a reaction, right? The tension pulling back up is what is holding this in place, right? And finally, draw the appropriate dimensions, right? So we have our radius here. That's it. Okay. So if we're going to draw the FBD for the bar AB of mass M, and a known force of P is pushing on it on the bottom. Okay, so let's walk through this one together. Okay, did everybody write down the steps for a free body diagram? I would definitely have written them down. Well, the first one is isolate the body. So here's my body, right? I was told that I want to draw the FBD for the bar AB. So I need to just isolate AB. So I'm going to imagine that I cut this all off. So this pin, this hinge right here, goes away. I'm just left with this, right? Step 2, coordinate axes. X, Y, in these directions, positive rotation. You can define this however you want. If you want Y to be positive downward, knock yourself out. If Y is positive downward, your sense of rotation also flips. So remember, it's always about the right-hand rule. But you can pick whatever coordinate system you want. And if as long as you list it there, I promise, and you're turning in work to me, I promise I will use that coordinate system to solve your problem, because that was the deal I made with you guys at the beginning of class a couple of days ago, right? But if you don't include it, I'm going to use whatever one I picked. Okay. Applied forces. In this case, what forces do we have? I've got P, and they told me it had some mass, so there's probably a weight, right? So yeah, I've got this applied force P, and this weight, which will signify mass times gravity. Okay. Okay. Replace our supports with forces. So I have a support here, right? And we'll talk more about supports really next week. But this is a pin support, okay? So let's assume this existed in the real world, and I'm going to say this is my beam, and I'm holding it at point C with a pin like this. Is this going, what is that pin doing? Well, it's holding it up, right? It's also not going to allow it to move away from the wall, right? It should hold it in this part, but it'll probably let it rotate there, right? And so we would say that this pin has an X component and a Y component force, but since it allows us to rotate, it doesn't create any moment there, so we'll just say it's Cx and Cy. Talk more about this, talk more about the different supports next week. Again, we'll talk about more next week. Okay. And then finally, put in our dimensions, right? And I just copied them from there. Now we have everything. Dr. D claims we have everything that we need to solve these problems. Yes, it does. It does say that. The free body diagram is a visual representation of Newton's second law, period, full stop. If we are going to be using Newton's second law to solve equilibrium equations, which we are, having them drawn, having all the forces that are acting on something drawn out for us allows us to very quickly and easily identify what's happening in the x direction and what's happening in the y direction. So if I say that something's in equilibrium, what does that actually mean? It means that the forces all balance each other, right? Remember, we went over it a little bit, but statics is really about when sum of the forces is equal to mass times acceleration is equal to 0, right? Which means that our acceleration would be 0. But if I say that the sum of the forces is equal to 0, that means when I add up all of these forces, they have to cancel, right? They have to be equivalent. If this is going to be hanging up in the air and not moving, right? If forget the force P, then the y direction, like I need to be, Cy has to be enough to allow me to hold the weight of the beam, right? When I start to push, if this thing is allowed to move, you can, it's only going to move to a certain point, then it's going to hit the wall, right? But Cx needs to balance P at some point, right? X and Y directions need to balance each other, okay? The how of a free body diagram, right? We talked about this. Imagine, I'm going to hit this again. Imagine that the particle to be isolated is cut free from its surroundings. In this case, right, we're going to use this thing from a bunch of slides ago. This is where the animations really hurt us. There. We're going to use this thing, okay? Remember this guy? And if we want to find, right, to determine the tension in the cables, and we know the weight, what are we going to do? Well, free body diagram. Okay, start here. We're going to cut this. I don't care about my reactions for this, right? I just want to know what the tension in the cables is. So I isolate the ring A, right? They got really easy and they made this an open circle. If I were doing this, I would just put a dot in the middle of the page, right? Because typically when we're talking about particles, I just draw a dot and I'm on my way, right? This is a particle. What do we have? Well, because we cut this cable, we have some force going along the line of the cable, right? Because that's how it works. Since we cut this cable, we have some force off of A going in the direction of D. And we have the weight, right? We cut this cable, so that weight gets transmitted through that rope, right? We know what this is, right? Right? We were told that we had a 40 kilogram mass, right? So how do I find the weight if I have a mass? Multiply by the acceleration of gravity, which on Earth is 9.1. Yes, thank you. 9.81 meters per second squared, which means that a Newton should be kilogram meter per second squared, right? Which is awesome. Great. So that's what first, right? Isolate your body. Second, show all of the forces that act on the particle. You need your active and your reactive forces. In this case, the active forces are the weight, and the reactive forces are the tensions in the cable, right? Then you're going to identify each force and show all the magnitudes and directions. Okay, so you put in your dimensions. Okay. Once you have this, I think it is pretty clear to see that FD does not contribute in the y direction to any of this, right? And so if I were to ask you how much of right? So this is carrying all the load. This needs to have enough y component to counteract this weight, right? If we're in equilibrium. If we're not, if we wanted this to move, we would need the y component of FB to be more than the weight. I don't know. Okay. Questions on FBDs? We're going to get a lot of practice with FBDs. Okay. I think there's a couple homework problems in homework 2 where it actually take you step by step through like interactive diagrams for FBDs. I think homework 2 should open tonight at some point, by the way. I think I set it to open after homework 1 was due. So probably open technically tomorrow at midnight. So if you guys want to get a jump, stay up till 11:15 and then jump on, right? And do not recommend. Get sleep. Sleep is important. Anyway, yeah, have a sleepover. Like it's like a launch party, right? Like you guys wait in the line at the Best Buy to get your Nintendo Wii. All right, 2D equilibrium. All right, first of all, questions on FBDs? Anybody? No, we good? You've seen this before? Stop being boring. Teach me something that I don't know. Jeez, so aggressive, guys. So aggressive. All right. So we're going to use this example again, right? We just made this FBD. Great. So since particle A is in equilibrium, the net force of A is 0. Remember, the idea is that this is satisfied. All right? The equation here, this needs to be satisfied, right? The sum of the forces has to be equal to 0 to fulfill equilibrium. This also means that the sum of the forces in the x direction have to be equal to 0, and the sum of the forces in the y direction have to be equal to 0. Remember what we said a couple minutes ago. If the entire system is in equilibrium, then the components of that system have to be in equilibrium, right? Which means that the x and y components would have to be in equilibrium as well. So we get this, right? And so we can write it this way, or you can write it in scalar form, right? Scalar form is just saying like, hey, I'm only going to look at the magnitudes of the x, and I'm only going to look at the magnitudes of the y. Remember, the magnitude can be negative, right? I don't really like thinking that as scalar form personally, because it's just looking, I think of it as, well, I'm just going to look at the I components by themselves, and I'm just going to look at the J components by themselves, right? It's a separation. But you won't include I and J in those calculations. The book likes to use E of E for equations of equilibrium. So this gives us in 2 dimensions, if we're just talking about forces, this gives us 2 equations, which means we can have 2 unknowns, right? And we can solve systems of equations. When we get to 3D, we'll have more. And then when we start talking about rigid bodies, we'll have more. But for a particle, this is where we're at. 2 equations, 2 unknowns for 2D. Yeah, what's up there? I always like to draw mine separately, specifically for so I like to draw mine separately just specifically for having the rotations mapped out, and we'll talk about that more when we get to cross products next week. But something like this would probably be fine for a 2D problem. So if we're going to continue with this example, right? We're going to write our scalar equilibrium equations. So if I sum my forces in the x direction, right? I should have FB times the cosine of 30 degrees minus FD because it's pointed in the other direction. And if I'm going to have sum my forces in the y direction, well, I've got FB sine of 30 degrees minus 392.4 because that's pointed downward. Turns out that gravity tends to point towards the ground. Turns out. Right. Solving, so in this case, right, this one's pretty simple. I think we would, let me say this a different way. I want to say pretty simple. I think the order of operations here seems pretty straightforward. The reason why you would want to solve this one first is because there's only one unknown in it, so you can solve it directly, right? So you move it over, multiply it by 2 because sine of 30 degrees is 1/2, and we end up with 785 Newton to the right. Great. And then we plug that in up here, and we solve for FD, and we get 680 Newtons to the left because it would come out negative. Well, no, sorry. It would come out positive, but it'd be to the left. So here's the thing. You're like, well, that doesn't make sense because it should be coming out negative, right? No. Remember, these are scalar equations. It's giving you magnitude. If it comes out positive, it's agreeing with the direction that you drew your vector, right? So what we have done in this case is we have assumed that this is operating in tension, okay? Why did we assume it is operating in tension? It makes the most sense that when pulling down on that, these lines would be in tension. Could you have solved it for compression? Sure, you could have the forces pointed in. And guess what? Both of these would come out negative and it would tell you, nope, I drew my vector in the wrong direction. Okay. A negative sign doesn't mean that it has the negative direction. In this context, it means I either chose correctly or I chose incorrectly. It gives you context as to how these should be directed, right? Since these both come out positive, it means that we chose our vectors pointing in the correct way already. If given an opportunity to choose, I would highly recommend, so the standard convention is to assume everything is in tension until it's not, right? And to assume, if you don't know the direction of a force, assume that it is positive. And this is the reason. If I get a negative out and I've assumed that it is positive, that means I need to put it in the opposite direction and it is in fact negative. If I assume that it was negative and I get a negative, that means that I was wrong and I need to make it positive. So you have a double negative, right? Which makes it less intuitive. So if you don't know, choose positive, okay? That would be my advice, because then the negative signs make sense, okay? But if you have a free body diagram, you should be able to reconcile what's happening anyway, right? Okay, questions on two-dimensional equilibrium as of right now? Have I confused anybody by saying anything? If I have, I apologize. Maybe I don't. I don't know. Depends on what I said. No. Everyone's all right? We're tracking. We're good. All right. What about cables and pulleys? Okay. All right. So if I have, turns out that if we say that we have a frictionless pulley, which is like the world's greatest invention, it turns out that in those conditions where we have no friction and the pulley has no mass, the tension on one side of the pulley should be equal to the tension on the other side of the pulley. And this stems specifically from the fact that it is one rope that goes through the pulley. Okay? Specifically in that case. So this tension and this tension should be equal. Cable can support only a tension or a pulling force, right? We talked about this last time. Like think of spaghetti, think of trying to push a shoestring or a piece of cooked spaghetti. It doesn't really work out really well for us, right? When we have lines, when we have cables, we want them to be in tension, which is one of the reasons why we always assume tension, because compression for cables is pretty bad, right? It's a bad thing to happen. Right? Tensions will always act along the line of a cable, right? So the magnitude of these two tensions is the same, right? But the direction is different, which is one of the other reasons why pulleys are so great, is that it allows us to change the direction of a force, right? With a known amount of force. Okay. All right, let's do an example problem. So I have this box. It's 550 pounds. And it has this geometry that I was given. And I am told that I need to find the forces in the ropes AB and AC. Well, that is two forces. That's awesome because I only have two equations that I can use. So that makes things a lot easier. Okay. Let's start with things that I know. What are my knowns? Well, they're kind of written up there already, but I'll just quantify them. I'm going to say that W, the weight, is equal to negative 550 in the J pounds. Now, I haven't drawn my free body diagram or drawn my coordinate system, but I'm going to tell you right now that I am going to draw Y positive upward, and I know that already. All right, that's really that and the geometry. I'm not going to list all the geometry that I know. That will be on my free body diagram, but the force is important. All right, so, and geometry. And we were asked to find, I'm going to call them very creatively, FAC and FAB. I know you guys are like, man. All right, let's draw our free body diagram. So if you're going to draw a free body diagram, a lot of you will be tempted to do something like this, where you just do that and you're like, I did it, Dr. D. No, don't do that. Draw your own, draw your own, don't draw it on top of this one. You can see very clearly that you cannot see what my free body diagram is trying to show you if I do this. Also, it's for a particle. It's not, and so we'll get, yeah, right. So I'll put the weight here. Straight enough. And then we'll have FAC going like there. And then FAB probably like there-ish. And it's not drawn to scale. It's good enough though. Your FBD doesn't have to be perfect. It has to make sense to you, right? Yeah. Something like that. And let me label it up with the pen now. So this is point A. This is my weight. This is F. A C. We're going to put our dimensions on there. This is a 3, 4, 5 triangle. And this guy here is 30 degrees, and that's FAB. And the last thing that we need is to define our coordinates. So there. A complete free body diagram. Has all of my forces, it has all of my pertinent dimensions, and I have my coordinate system so I know which is positive and which way is negative. I'm going to get myself a little bit more room here. Look at that. Man, it's basically twins right there. And barely tell the difference between these two. Barely. I'll move these guys up over here. Okay, so what do we want to do first? Well, this is an equilibrium problem. So we were asked to find the forces FAC and FAB. I guess we'll start, let's sum the forces in the x direction, I guess. Doesn't really matter how you want to start it, right? But if I sum the forces in the x direction and I set that equal to 0, I will get negative FAB in the I. Why? So we're going to do the scalar version. Don't write the I. FAB plus FAC, and these are x components, right? Okay. That's not really super helpful, right? Mainly because it doesn't tell me, like if we write this down, it's going to create 4 unknowns, right? Because I'm going to have FACX, FACY, FABX, and FABY. So let's just cut to the chase and we'll use the geometry that we're given to figure out what these components should be. So we have negative magnitude of FAB cosine 30 degrees plus 4/5 FAC, right? And that's equal to 0. And I'm going to call this guy equation 1. We sum the forces in the y. We got FAB in the y plus FAC in the y minus the weight. And notice I didn't put the y component for the weight because there's only one component for the weight. We know the weight. So if we rewrite this equation, right, we'll get FAB sine 30 degrees plus 3/5 FAC minus 300. Equation 2. 2 equations, 2 unknowns, right? Yeah. 550. Thanks. I don't know why 300's in my head. Like I said, 550. This is the last problem we did had a 300. Okay. Good catch. 2 equations, 2 unknowns, right? Solve it using your favorite method. Okay, so you can use substitution. You can use the fancy one where you stack them both and you do elimination, right? You can use MATLAB. You can use your calculator. You can do whatever. In this case, I started with solving equation 1, right? So if I solve equation 1, I end up with what? Well, if I move FAB cosine 30 over to the other side, right? I get FAB cosine 30 degrees is equal to 4/5 FAC. So I can come up with an expression for FAB, which is equal to 4/5 FAC divided by the cosine of 30 degrees. So that's kind of gross, but that's fine. You can plug in the numbers, right, for cosine of 30. I'm going to leave it for now. You'll see something in a sec. But if you had gone ahead and plugged things in for cosine of 30, it's just a number. You can do that. Then we're going to take that and we're going to plug that result in up here, right? And if you do that, you guys gonna be able to see it if I draw it down there. I guess we'll find out. You get 550. Can you guys see that? Okay. 550. I'm just moving the weight over, right? I'm preemptively moving the weight over so that it is non-zero on the left-hand side times what's equal to 4/5 of sine 30 degrees over cosine 30 degrees times FAC. So when I plug in 4/5 FAC divided by cosine 30 degrees into FAB, notice I get sine over cosine, which reduces the tangent, right? Now, is that a big deal? No. If it was 45 degrees, yes, right? There's certain reasons why you would want to keep one or the other. It doesn't really matter in this case. Plus 3/5 FAC. Okay. Guess what? You can multiply both sides by 5 to get rid of the 4/5 and 3/5. All right, so we can do that. This time I am going to move this stuff. Give me a second. Come on. There we go. Okay. So now we're here, right? We'll multiply both sides by 5. So you get 5 times 550 is equal to 4 times the tangent of 30 degrees plus 3 whole thing times FAC. Then guess what? Divide by 4 times tangent of 30 degrees plus 3. And we can find the FAC. Okay. So notice that that came out to be positive, which means it agrees with the direction that we drew it in, which means that FAB is in fact going to the left and up. Okay. And you might see some people like do that just to indicate we know that it goes to the left and up. Okay. Then we take that and we go back to this equation, right? And we plug in our 518 in there and we solve for FAB. Oh. So FAB times the cosine of 30 degrees is equal to 4/5 times 518. Divide both sides by cosine of 30, right? . You get 479 pounds. And that also came out positive, and so we know that FAB, well, I drew FAC in the wrong direction. It's this way. FAC goes that way. So we chose the correct sense with tension. We're good to go. Right. Simple two equations, two unknowns, right? Everybody cool with solving a 2x2 system of equations? Yeah, yes, not hearing anything. Good, I got a thumbs up. Cool. Is it time consuming? Yes, for sure. Are you going to have special tools on your quiz to deal with this? I mean, if you're allowed to use a calculator. I didn't say that you can't use a graphing calculator. Does your graphing calculator do that? Then yes. Mine, well, I have a TI-89. I've had it for 30 years. It's great. Yeah. Titanium edition. It's great. Anyway, you can use you can use your calculator to solve it if you want. These don't take that long to do in a 2x2, right? Where that really buys you time is when you have like, I would say even 3 equations and 3 unknowns is not that hard, not that difficult or time consuming. Anything bigger than 3. So systems of 4 equations or more, you kind of, the problem is in this class, it kind of goes from 3 to 6 to 9, right? And so 6 equations and 6 unknowns, I would definitely recommend using a software option to do that. For sure, 9, definitely. Anything higher than 4 becomes really tedious otherwise. 4 is doable, is the edge of doability. Same deal as when you're walking up flights of stairs. 4, it's fine. Anything more than 4, you take the elevator. It's diminishing returns beyond that point. All right. Any questions on this? Yeah. Okay. Mhm. If not, if they have friction, because the friction going through would cause slippage in the line. Could. It's because I'm trying to think about like in the gym when you have like crappy equipment, like it feels heavier against stuff. So if there's some stiction, yeah, if it sticks on the pulley, then you're gonna end up having more force on one side than on the other. Right? No. And then the problem with that is it's not just the tension that has an issue when there's friction. It's also the force on the bearing in the center of the pulley increases. And so you tend to end up having a failure at the pulley itself, as opposed to like, it takes a lot to have the cable snap. It takes way less to have your bearing break, right? And so that's where you typically see the failure there, because having friction in the pulley creates undue stresses and strains at the connection point. Right? But it can cause slippage. I think an easy way to visualize it is if you've ever ridden an escalator, if you put your hand on the rubber part and you just do this, like just really crank backwards on it, it'll cause the entire thing to slip. And that's not having even tension for a moment in that band, right? It's misspent youth for sure. All right. Okay. Any other questions on all right. Smooth contact. Okay. So, all right. So in physics and in this class and in dynamics and in biomechanics, right? And in probably in circuits too, right? Really any class where there are actually losses in a thing. We like to make these grand shows of saying, well, neglecting friction, neglecting wind resistance, neglecting any heat that your circuit would create, right? Like all of those things where there's energy losses in our system, we tend to try, we're going to start off by mostly ignoring those things, right? Why? Because they're nonlinear and they make our lives a little bit more difficult. But in the case of smooth contact, if an object rests on a smooth surface, then the surface will exert a force on the object. Okay? We call that a normal force. It is always perpendicular to the surface that the object is touching. And that is why it's called a normal force, because in mathematics, the term normal means that you are perpendicular to something. It has nothing to do with that's what we're expecting, right? It's not called, you wouldn't call it a typical force, right? It's a very mathematically derived definition, right? So in this case, where we have whatever this is, some sort of roller on a 30-degree incline, because that's what we're doing. The normal force would be perpendicular to the incline, right? Which means that we need to do a little bit of geometry to figure out the angle off of the X or Y that we're looking at, right? In addition to the normal force, this cylinder is also subjected to weight and to tension. Okay. A lot of people will try to tell me, and the reason we use a 30-degree incline here and not something flat is because if it were flat, the normal force and the weight would be the same, right? Well, they should be. I mean, just look at, you guys all have stuff on those tables right now. If the normal force and the weight were not the same, either your computer would be floating, right? Or the table would be crashing into the ground, right? One or the other, okay? When we look at it in an angle, though, now that normal force has X and Y components, and only the Y component of the normal force corresponds to the weight. There's still an X direction component, right? Which in an unbalanced system is what causes motion, because if it's larger than the amount of friction, but in this case, there is no friction, what's going on, right? The tension, X direction tension has to be balanced by that normal force, okay? So be aware, you can't just say that the normal force is equal to weight. If there's an angle, we need our free body diagram. Like if you had the free body diagram, it's very clear here that Y direction is not just the weight, there's more going on there, okay? Springs. Everybody loves, springs are the best, right? Spring force is F equals to K. We're using S in this class, which is interesting. Most of the times you'll see F equals KX, but S is fine. It doesn't have to. I mean, in this case, it would be, I would say this is Y, right? It's whatever the distance is. The delta. It's really a delta from the undeformed length, right? So keep that in mind as well. But there you have it, right? So we have a spring. Think about it this way, right? If I were to hang a mass from the ceiling, which if it were in equilibrium, right, that spring would stretch enough to allow that to hang at some level, right? Because what's creating that force is the displacement of the spring, right? So again, with a free body diagram, right, you'll be able to understand what those forces look like. All right, this one is fun, right? We're gonna do this one. All right, so I've got this lamp here, which really just looks like a bowl that somebody like spray painted yellow, but it's a lamp. So there we go. And it has this very elaborate rigging system that holds the lamp up because reasons. The lamp, it has a mass of 20 kilograms, and it is in the geometry shown here. And we are asked to find the forces in each of these cables. Okay. And by each of the cables, we're talking about all of the cables. So cable DE, cable DC, cable AC, and cable AB. Because we already know what the force is in cable FD, because it's the weight. So this is asking us to find all of those things. So that's 1, 2, 3. That's 4 things that we were asked to find, right? So I'm going to just write that down real quick so that I don't forget. So we known, the mass of the lamp is equal to 20 kilogram. And we are going to find FDE, FDC, FCA, and FCB. Okay. That is 4 things. And I have 2 equations. Seems like I'm not going to be able to solve this. You have 2 equations per free body diagram. Dun, dun, dun. The implication being that you're going to have more than one free body diagram to be able to solve this. So, all right, let's imagine just for a second that we're not worried about point C. We're just looking at D. Well, we did this. We've done this problem. We've done it 3 times now. We did it one time when it was called A, B, and C, and another time where it was just before when the box was hanging there, and we did it with the cylinder thing, right? And so this is one that we've seen before. So what happens? All right, so we're gonna start. Let's draw a free body diagram. Let's do that. Or our FBDs, 2 of them. Okay. So if I start with the FBD for point D, here's point D, very cleverly drawn as a point particle. We're going to call this one FDE, and that's at 30 degrees from horizontal. We've got our weight, which is the weight of the lamp, which is equal to the mass of the lamp times gravity. And we've got this, which is completely horizontal. This is FDC. And I'm going to draw my coordinate axis over here. With my X and Y. And I wonder if I give you guys a few minutes, you can draw the FBD for point C. Take a couple minutes. I'll get you started. There you go. Mhm. Mhm.
Doesn't want to be on the table. He wants to be
Yeah,
there.
yeah, yeah. Everybody doing okay? Question? Yeah, sorry.
Distinction, in my country. What is that for? It just means that 453 is that's the triangle, like it has
Yeah.
the same angles as the 453
Yeah.
triangle. Oh, okay.
Yeah, it's saying that there's a similar, there's a 3, 4, 5 similar triangle there. Mhm. You guys good? Got any questions? Anything? You guys good? Good. Everybody good? Questions? Anything? Lonzo? So it depends on which direction you're gonna have it pointing in. So if the way that I use that notation is that if they should be the same, they're just equal but opposite directions, right? So if I'm going from, I call it CA because I'm going from C to A.
You don't have to call that.
No, you can call it whatever you want, really. But you remember that that's the direction that
Yeah.
the vectors. Well, you guys good? Yeah. All right. All right, everybody good? Maybe? Any questions? No? All right, so what's your free body diagram look like then? Yeah, that's a fun question. Like, describe it to me. No. So, all right. So we should have FCA in the direction like that. And we know that it is a 3, 4, 5 triangle. And then we've got FCB. And this is at 45 degrees to the horizontal. All right. And then we've got what I'm calling FDC still. Notice that I have those two forces pointing towards each other. They are equal but opposite. Why? Well, we'll talk more about it when we talk about internal versus external forces, but because you cut the line there, right? Imagine this. That right now, those things are in tension, right? And they're pulling away. And if you were to cut it in the middle, right, this whole thing would fly apart, right? So clearly, there is an invested force, an inherent force in there that is pulling those two things back together, right? So they have to be pointed back at each other. Now, if you had assumed that FDC was in compression instead of tension, that's fine. But that would also mean that the other side would need to be in compression as well, which means they would need to be pointed opposite of each other. Okay? We'll talk more about internal forces next week, right? But that's the gist of it. Okay, so now we've got our FBDs. We should probably start doing some equilibrium equations, right? So do we want to start at D or do we want to start at C? What do you guys think? Why? Yep, we have more knowns. In fact, the other one, we don't know anything. So we would have to solve it all symbolically and then go back to D and solve all that and then go back again to resolve that, right? So order of operations, let's start with D. We know the weight. We can figure out the rest, right? 2 equations, 2 unknowns. So let's start. Sum of the forces in the x direction is equal to 0. And also, notice I drew one coordinate system for both of these diagrams. And I did it very strategically in the middle between the two diagrams, right? Okay. There it is. Okay. If I sum the forces, I get negative F dc plus F DE cosine 30 degrees. Yep. I'm gonna call that equation 1. I like to keep track of my equations by numbering them. It helps me later because in this one we're gonna have 4 equations and then you don't have to worry about which one is which, you just already know. Okay, in the y direction I have negative weight of the lamp plus FDE sine of 30 degrees. Call that equation 2. Well, it's our lucky day because we're just going to solve equation 2 directly, right? We've got everything we need to solve for FDE right in there, right? We know what the weight is. Well, we technically know what the weight is. We have the mass, right? So if we wanted to know what the weight is, that would be the mass of the lamp times gravity, which would be 20 kilogram times 9.81 meters per second squared, which should give us roughly 196.2 Newton. And remember, Newton is a kilogram meter per second squared. Because why? Because when they came up with the SI units, that was the derived unit. And if you're going to have something that is a mass times an acceleration, then it should be a combination of both mass and acceleration units. That's why. There's also fun unit conversions that you can make way down the road to get newtons. We're not going to do them in this class, but you can determine a voltage. You can make an equivalent voltage to a newton, which is really bizarre that that exists, but it does. You can do it. Anyway, let's keep going. Okay. So the weight divided by sine of 30 degrees is equal to FDE. So it turns out that FDE is twice the weight. FDE is equal to 196.2 divided by 1/2, which is equal to 392 Newton. Great success. I'm going to write that up here so that I have it for later. So far, so good, right? We're going to take that and we're going to put that into equation 2, right? Because if I throw that into equation 2, then I just solve for FDC right away, right? So FDC, if I manipulate equation 2 just a little bit, sorry, I mean equation 1, sorry. Move FDC to the left, I get this equation. Right. So what does that come out to? That's going to be pointed that way. You can, if you want. Typically, what you'll see is it is, unless you put it back into vector form, this is just considered the magnitude, and you have to understand that if because we got it positive and we drew it to the left, that means it's agreeing with the sense that we gave it already. Because remember, when we wrote these equations, we already accounted for the positive and negative base we drew. Question. Okay. So that's for point D. I'm gonna get rid of that. Keep this. So I'm gonna keep these two over here, right? And there. All right. Anybody have any questions on that point D, the analysis of point D? Everybody good? We're tracking. And now it's just rinse and repeat, right? This one's a little bit more involved because there's two angles instead of one. Yeah. Go. 392. 196.2 divided by 1/2 is 2 times 196.2. Turns out that when I touch the screen with my hand, these are all, well, I could just draw on it if I want. Maybe I'll do that. Maybe it might turn out better than using the pen. I don't know. Okay. Sure thing. Okay. So rinse and repeat. You guys want to sum the forces in the x direction first or the y direction first? We get crazy. We can go y direction first this time. I don't know. Stay the same. Here, all right. Direction. Notice this time that FDC is positive, right? And then we're going to have two components here. We're going to have FBC as a negative component, the sine of 45 degrees, and we're going to have 3/5 FAC. We'll call that equation 3. And we'll do our y direction, same deal. This one's going to be, well, FBC or CB, however you want to call it. I guess I used CB over here. Should probably maintain my own notation. So, not that it matters since it's 45 degrees, whether it's sine or cosine. So if you mess up sine or cosine on that one, doesn't really matter, right? Doesn't be the same. And the points are always yours to lose. Sorry. All right, so what do we got going on here? Well, the same thing, right? So this one, unfortunately, there's no really good place to start, right? Because on the side that we know the force, we still have two unknowns. And both equations have two unknowns, right? So we kind of just have to pick one and go for it. Right? We have to just kind of pick one and go. So is substitution the best and fastest way to do this? No, actually, elimination is. And why is that? Because FCB cosine 45 and FCB sine 45, they're the same thing. We just have to multiply 1 by -1, and then we're off to the races, right? So let's go ahead and try that out. First thing I'm going to do, however, is I'm going to move this over. So it's going to be FDC is equal to FCB sine 45 degrees plus 3/5 FCA, and 0 is equal to negative FCB cosine 45 degrees plus 4/5 FCA. And if you add these two together, these go away. And we're left with FTC is equal to 7/5 of FCA. Is everybody tracking with how I did that? We good? Okay. Which means that FCA is equal to 5/7 of FDC, which is 5/7 of 339. And so I'll write it up here, FCA should be equal to 242, right? Yep. You can view it however you like. I prefer to use, so we talked about it earlier, right? The reason why I would suggest using fractional instead of decimal is that you, what? Oh, Desmos? No computers for the exam. Sorry, I thought you said decimals. My bad. Yeah, no computers for the exam. Quiz, sorry. No. No. All right, anyway. What direction is that going to be in? Well, it came out positive, so it'll still be in tension. All right. All right, so cool. So we did that. So now what do we have to do? Well, we got to plug that 242 into either equation 3 or 4. It doesn't really matter. It should get us the same value. I'm going to choose to use equation 4, mainly because there's just fewer terms. That's really it. There's nothing crazy about it. So if I plug this into equation 4, I get FCB cosine 45 degrees is equal to 4/5 FCA. All right, just rearrange that equation a little bit, move things over to the left-hand side. Solve for FCB since that's what we need. FCA we found was 242. Divide it by cosine of 30. FCB comes out to 274 Newton. And that's also going to be in the original direction, so down and to the left. Sorry, it should be 45. 45, sorry. It's too many problems with different cosines that are just rent-free in my brain right now. My bad. Good catch. Cool. So I hope that you guys would agree that this isn't particularly, at this point at least, the math of this is not particularly difficult, right? And it's just like I told you the other day. It's really an exercise in bookkeeping, right? Making sure that we have everything set up, because math-wise, what have we really done? We've done some trig. That's really too about it. Like, I know algebra is, it's a big ask to do the algebra for sure, but I feel confident that you guys can do it 100%. But yeah, that's really it. And that's the essence of these calculations for equilibrium, right? Remember, the thing about particle equilibrium in specifically is that we are only really concerned about forces, right? Later, when we talk about rigid bodies, we have to be concerned about some other things that we'll talk about. But for right now, 2 dimensions, you have 2 equations. You can sum the forces in the x direction, sum the forces in the y direction. So order of operations is draw your free body diagram, sum your forces, set them equal to 0, solve 2 equations, 2 unknowns, make sure that it tracks with what you drew, right? Okay. All right. Now we get to do some fun stuff. So it turns out that 2D problems are great. And there are times in the real world where we're interested in just 2D things. However, there are also times in the real world when we're interested in things that exist in 3 dimensions. And if we were higher level, higher dimensional beings, I'm sure we would be concerned about 4 or n dimensions, right? 1, n minus 1, whatever you are. No, anyway. What do we need to be doing here? What kind of skills we want to develop for this? Well, a 3D free body diagram and applying 3 scalar equations based on 1 vector equation. So if you thought to yourself, doing the sum of the forces is super fun in 2 directions, we're gonna do it one more time, guys. It's gonna be great. It's gonna be your new favorite for sure. So here's a question. In 3D, when a particle is in equilibrium, which of the following equations apply? Sum of the forces in the x in the I direction plus some of the forces in the y in the j direction plus the sum of the forces in the z in the k direction is equal to 0. Sum of the forces is equal to 0. Sum of the forces in the x is equal to the sum of the forces in the y is equal to the sum of the forces in z is equal to 0. All of the above or none of the above. All right. What do you think? Who thinks A? Thinks B? C? D? E? You guys all went with the driver's ed answer. It's E. It's D. It is, all of them. These are all the same equation. No. No, I don't know. I went with the red box. It's important. Um, Monday, by the way, just to let you guys know, Monday when we do these, I will have whiteboards and markers for y'all, so you can write your answer down. We don't have to do the show of hands anymore. You just write it down, and then you hold it up. Right? It'd be so great. It'd be like a game show, basically. All right. All right. So what do I have here? I have this shear leg derrick, not to be confused with the bow-legged derrick, to be designed to lift a maximum of 200 kilogram of fish, because it's important. Yeah, when you're fishing. How would you find the effect of different offset distances on the forces in the cable and the derrick legs? Oh man. Well, we do live in a 3-dimensional world, I'm told. But I mean, we're going to need a free body diagram here, right? And presumably, because of the way that this is created, this was designed, because these split out in the x direction, we have forces that are going to be in and out of plane, right? Because that's the way that this is designed. We're going to have tension here, but this is there in case the fish start to sway from side to side or front to back, right? All right. So that's 3D systems of forces. Turns out that sometimes we have forces that exist in 3 dimensions. Right, great. So how do we do equilibrium for them? Same way that we do them in 2 dimensions. It's just an extra step. And so now instead of 2 equations and 2 unknowns, we will have 3 equations and 3 unknowns, right, per free body diagram. per free body diagram. So you can see how this might get pretty crazy pretty quickly. So, right, we're going to sum the forces in the I, J, and K direction. This also gets sloppy, and sloppy is a technical term, when you are talking about drawing these things, right? It's not easy to draw certain things in 3 dimensions, right? So just do the best that you can, right? Vector equation will be satisfied only when the sum of the forces in the x, y, and z directions are equal to 0 independently. These equations are 3 scalar equations of equilibrium, just 2 scalar equations in x and y directions. If we wanted to include a 4th dimension, we could do that, but I don't think that that would be wise. So we're not going to. Also, we don't live in a 4-dimensional. Well, if you count time, fine. Anyway. Thing about statics is should be the same over time for the long haul. All right. Valid for any point in equilibrium and allow you to solve for up to 3 unknowns. Great. Let's do one. And this is probably the only one we're going to be able to do today. 3-dimensional problems take longer than 2-dimensional problems. Okay. This drawing is actually not too bad to kind of see what's happening, but it's also not a free body diagram, right? And it's not a free body diagram because I can clearly see the hooks in the wall that are holding these cables in place, which means I have not detached the body from its surroundings. All right, so we're going to draw a free body diagram for point A. Let's do that first. Do that first. Okay. So I'm going to call this tension A, B. Okay, and the thing about it is, look, that is purely along the x-axis as it has been defined in that picture, right? So we should be expecting that this force has only an x component. And I'll draw my coordinate system at the end. Okay. That one's going to be TAC, and we'll draw some stuff in there for when we get to our dimensions in just a second. The nice thing about weight is that we are going to assume that that just goes straight down. And that's not really an assumption. That's just how weight works. I guess the assumption here is that that's the ground, right? That's pointed down towards the earth. If we were looking at this upside down, the weight would be pointing upward, which it's not. So anyway, there we are. Stupid. All right, and then the last one's TAD, which is somewhere over here. So I want you to notice a couple of things about the dimensions that we are given on this diagram. First of all, the weight and TAB, great, fantastic, love those. I know that that was in one direction and one direction only. TAC, that's annoying because that's that double, that's gonna have to be where we do a projection down to the XY plane, and then we do the components of that other vector. That's annoying, right? TAD, this is magical. They have given you the actual angles from each of the axes directly. So you just need to do one trig step for each of those using the correct angle, right? So let's start off with, well, let me finish this free body diagram, right? Because I didn't finish it yet. So here's my coordinate axes. We've got X, Y, and Z, right? Here's my positive rotations. And again, for right now, it's not that big of a deal, but next week, it's gonna mean something more for us. Okay. It's always right-hand rule to define the rotation. So x into y into z, z into x. That's what I'm looking at for my rotations. Okay. We have this angle set as 30 degrees and this angle set as 60 degrees. We have an angle of 45 degrees from the z-axis, an angle of 60 degrees here, and an angle of 120 between these two, because this is my x-axis here. And I think we should be ready to roll with this as is. Did my best. I did my best to draw it well. I don't know. I feel pretty good about that. Feel pretty good about it. Sorry. There. Okay. I mean, I'm going to do a couple of things before I start jumping into equilibrium equations. The first thing is we didn't write down what we know yet, right? So what do I know? Well, I know, let's call it F sub A is 300 pounds. It's actually negative 300 K pounds, right? Pounds in the K, I guess we're going with today. That's fine. That's really the only force that we know. I'm going to write the vectors for the other ones though, right? Because we know that TAB is going to equal TAB in the I direction, also in pounds. TAC. Well, that one is annoying because remember, what do we have to do? Well, that 60 degrees is off of the x-axis, right? So if we have the sine of TAB sine of 60, or sorry, TAC sine of 60, right? What's that going to get us? That's going to get us the K component, right? So let's write that down here. TAC sine of 60 degrees in the K. Okay? That's this blue one over here. Do we see where I got that from, right? If I use this triangle right here, right? So now I need this base, okay? And that's going to create its own triangle because now that's down at a 30-degree angle in the XY plane, okay? So I'm going to draw it over here, right? So now we have this vector, right? And if I take this vector and I want the y component of that vector, right? Well, I first had to make the cosine of 60 for it, right? So TAC cosine of 60 to get me down onto the floor, right? And now it's also the cosine or the sine of 30 because I want this component, right? But it's going to be negative because it's pointing in the opposite direction. This is where it gets complicated, huh? I'm going to move that for a second. So we start same starting point as before, TAC times the cosine of 60 degrees, right? Because that gets me to the, remember, projects TC down to the floor, right? And now I need the y component. Well, that's the cosine of 30. I should have written sine in the last one, huh? Please hold. That's going to confuse people. Let's backtrack. This one, I'm telling you, this is where it gets tough. Okay. So this is my original vector. I break it down into two components. I break it into its z component, which is the sine of 60 degrees, right? The cosine of 60 degrees lays it flat on the floor, okay? Now, if I want the x component of that, I need to take the sine of 30 degrees because it is this back leg right here, right? Because here's my x-axis. We also know that it's pointed negative because when we lay this down, we have a vector that is going negative x and positive y, okay? So everybody track in with me on how we got this term here. So the cosine of 60 drops us to the ground, and then we are using this new triangle to figure out what proportion of this vector gives me the x direction part, okay? We do the same thing here, except that it's going to be a double cosine now, right? Because now to get to the y, we need the adjacent side, okay? And that one's going to be positive. And then I'm going to move this guy back over here because that's positive, right? So we found the k component first, then we found the x and y. But we had to use a double trigonometric identity there. Well, it's not an identity. We had to use double trig because there's two triangles, two right triangles that control those vector projections. Okay? Is everybody tracking with that? Because that's going to be the hardest part on this particular problem. It is. And I get it. It's a weird thing to visualize, right? But think about breaking it down into corresponding triangles, right? I think that's kind of a helpful way. How many different right triangles you have, Barrett? Yes, yes. Sorry, let me get that on there for it. Yes, exactly. Sorry about that. Okay. TAD. This one's way easier. Why? Because they were super nice and they gave us all the angles that we need to go directly to the axes that we care about. That's why. So in this case, we have TAD. Well, if I want the portion of this on the x-axis, well, that's the cosine of 120 degrees. How do I know that? Because there's 120 degrees between this vector and the x-axis. And technically, you could use any of them to find the z-axis if you really wanted to, but I would just use the angles that you're given, right? So cosine of 120 degrees, that's the I direction. The j direction, this one's actually going to be negative, right? In the j direction. And it should be the cosine of 60 degrees. And like I said, that's going to be negative. And then finally, cosine of 45 degrees in the k. We've got all of our vectors lined up now. It's essential to do this part, right? Why? Because if we are going to sum the forces in the x, y, and z, or the I, j, k directions, we need to know what all the components are for each of the forces. Because right now, as we have this lined up, we can write one equation with all of our I components, one with all of our J's, and one with all of our K's, right? And then this will fall out, right? So you don't have to write a resultant vector. You can if you want. It's going to be super long. You don't have to. Nobody's asking us for a resultant vector. They're asking us for the individual components. Okay. So if I sum the forces in the x direction, set that equal to 0, what do I have? Well, I got TAB minus, well, if you do TAC, right? The cosine of 60 times the sine of 30, those are both 1/2. So minus 0.25 TAC minus 0.5 TAD. Okay. Equation 1. We do the same thing in the y direction, right? Equation 2. All I did was calculate the sines and cosines, right? That's where those decimal points are coming from. And in the z direction. Okay. Three equations, three unknowns. This one is going to be easiest to do a substitution. The way that I did it, and you can do it however you like, but my number one rule with doing any mathematical solutions is do the one with the least number of variables first and then move around until I can get it down to 1, right? So I would start with equation 2. Do this. Yeah. You can do whatever you want. It doesn't matter. You can do it however you like. My brain just went to, I can't solve. So first thing I look for is, can I solve any of these directly for anything else and just plug it in? And the answer is no. I can't just, there's not one equation that will just give me a numerical value. And so then my brain goes to, okay, well, equation 2 has the least number of terms that I have to carry. Let me just do that. Right. But it doesn't matter. You can solve them in any order you want as long as you're not substituting into the same equation that you just subbed into, right? As long as you don't do, well, I solved equation 1 for TAD, TAC, and TAB, and then I subbed all of those things into equation 1, right? Then. All right, so if we solve equation 2, and feel, again, you guys, there's multiple numbers of ways to do this. We say that TAC is equal to 0.5 over 0.433 TAD. And so TAC is equal to 1.155 TAD. I know we're over, and I apologize, but we're almost at the end of this, and I don't want to leave it over the weekend to just have to redo the entire problem again when we get back. So, because that's what will happen, 100%. So we'll be done in a minute, I promise. I'm going to erase the top of this right now to give myself some more room, but yeah, sure thing. You guys let me know what that is. So if we solve equation 2, that's where we're at. So I'm going to take equation 2 I'm going to take this equation or this thing that we just solved, and I'm going to plug. Oh, what is going on? Just put it there. Just leave me alone. Leave me alone, ghost. Yeah. I'm going to plug this into 3. Okay. Why? I, because then I actually can solve for TAD, right? If you plug it into 1, then you have to do another substitution, and it allows me to actually get a number, and that feels like a win, right? It feels like a win. All right, so if we do that, I rearrange equation 3 a little bit to move the 300 over. That's going to equal 300 is equal to 0.866 times 1.155 times TAD plus 0.7071 TAD. Well, that means that, right, if you do all the decimals out. And so obviously without a calculator, that would give you 176 pounds. And I mean, I guess if you had to use a calculator, that's fine, but I would expect that most people don't need it for that sort of math. So good thing I found this notebook in the parking lot. All right, so we found TAD. That's great. We can now substitute that into equation 2, right? So we're going to go back to equation 2. We're going to substitute that in, and we'll get an answer for TAC, right? Into equation 2. And so now we've got 0.433 TAC is equal to 0.5 times 176, right? Everybody sees where that came from. I'm taking liberties with solving these things pretty quickly and just doing the algebraic manipulation. Hope that's okay. If you need me to run through it, let me know. And I can certainly do that. If I divide that by 0.433, we find out that this is about 203 pounds. And then I take TAC and TAD, and I plug that into equation 1, right? And so we are looking for TAB. So TAB is equal to 0.25 times TAC, which is 203, plus 0.5 times TAD, which we said was 176. And that gives us 139 pounds. Great success. Crowd goes wild, right? Because most of us do math with a crowd watching us, bated breath. And there we are. All right. Sorry that we went long. I try not to make it a habit. I do think that it was necessary in this case. Okay. That being said, I got a poll everywhere for you guys. There you go. First off, how's everyone feeling so far with class? If I will say that if you are in the red with this, you should definitely be come to my office hours and we'll talk about it. Okay. And if you're not in the red, you still come to my office hours when you talk about it. That'd be great. We will be doing a lot more 3D problems next week. And they just take a little bit longer. They just take a little bit longer. All right.
Extension, until I get my contact.
So I can't do that until you get your account back. So
Okay.
we'll
Yeah,
have,
that's
we'll,
fine. It's
yeah.
like when I get my account.
When you get your account back, we'll figure it out.
Okay, thank you.
Yep. Oh, thank you. If I don't see you guys, have a great weekend.
Still time to tell me on this.
Mhm.